to place a straight line equal to any given straight line at a given point. Explain what that means. So again, equality of lines should be interpreted as equality of length. So the idea here is the following. So let A be a given point. Say here. And BC a given straight line. So like this, for instance. Now if B is equal to A or C is equal to A, then I'm done, right? So I just need to construct a straight line of the same length as BC with one of its endpoints at A in any direction. Okay, so I might as well assume, as in the picture, that B and C are not equal to A. And so here we go. So we draw the line AB, and that's by postulate 1. And then we're going to use proposition 1 to erect an equilateral triangle with that as one of its sides. So it's D. Okay, so then we extend, so remember by, which axiom was it? Postulate 2. We can extend DA and DB. To DE and DF. So I should move my A and my B. Now, exactly how long DE and DF is, this is a bit of a sore point in my opinion, but retrospectively we can look from the end of the proof and see that we just need to make it larger than the radii of certain circles or whatever. So I don't want to dwell on this. There is a related point, which is some of the proofs involve arguments like choose a point on a line, which is kind of a little bit dubious, it seems to me, on its face, but again, we won't worry too much about that. Okay, so we extend these lines, and then we're going to construct several circles. So the first circle we're going to construct is a circle with center B and radius BC. Okay, so maybe I'll do that in blue.
I'm wondering if could you make the BC line look different to the in length to the AB line?
Yeah, I think that's a good idea.
It's somewhat similar.
Seem okay?
Yeah.
Okay, so construct a circle at B of radius BC. It's not awesome, but whatever. Okay. And then we're going to call this point here G. And I don't need to name any of the other points, I believe. Call G the intersection with DF, let's say. And then we're going to draw a circle at center D with radius DG. So construct circle at D with radius DG. That goes off much further.
Is it important that you say G is the intersection with DF rather than BF?
Yeah, interesting point. So DF was defined as continuing DB, so we would believe those are the same, but you're asking, is that actually deducible? Well, BF is, there's only one line between any pair of points, so those must be the same. So as a consequence of that postulate, G could be defined either as the meeting point of the circle with DF or with BF.
Mm-hmm.
Okay, so we've got the second circle at D with radius DG, and I'm going to call the intersection with DE L. So that's over here. Okay, so now maybe I should shift over to the second board. Also, I'll say the following out loud so you can keep your eye on the diagram, perhaps, is the best way to do this. Okay, so since B is the center of the circle, which has center, so the way the reference does it is to introduce, they name circles by 3 points, so they introduce some random letters to stand for some other points on the circle. Maybe I'll just avoid using these names and see how I go. So BC is equal to BG. And so this is by definition of a circle. DL is equal to DG. The same. Now within these, dA is equal to dB. Right, that's by construction, so that's by, if you like, proposition 1.1. Now, one of the common notions says that if you subtract equal lengths from equal lengths, how should I say this? The remainders, so BC is equal to BG, and DG is equal to DL. So since dA is equal to dB, if I subtract dB from dG and dA from dL, those remainders have to be equal. Right? BG has to be equal to AL. Maybe let me see exactly how this common notion is phrased, since I think not saying it very well. So common notion 3. If equal things are subtracted from equal things, then the remainders are equal. Yeah, that's... If equal things are subtracted from equal things, the remainders are equal. So this is a hypothesis on the interaction between addition, or rather subtraction in this case, and the equality relation, right? So hence, since hence BG is equal to AL, and since BG is also equal to BC, we have AL equal to BC. So this is by common notion that common notion 1, which says that things equal to the same thing are also equal to one another. So transitivity. Okay, so what did we do? Well, we've constructed a line starting at A, the same length as BC. So that's as required. All right, any questions about that? So you notice here that E and F don't play any role, right? So they simply need to exist in order for us to introduce the letters G and L to denote some points. But it doesn't matter where we choose them as long as we choose them sufficiently large. Right? If they were chosen in between, if F was chosen in between B and G, then the definition of G wouldn't make sense as an intersection. So there is some requirement that it's sufficiently large, but
Can we
it's interesting, like how
Oh,
little
sorry.
symbolic manipulation there is.
how what, sorry?
How little symbolic manipulation there is. Like my first instinct would be to label the diagrams with like modern geometry notation, like label the side AD like lowercase a or something.
Right. Yeah, it's kind of interesting. I think, so in Euclid you'll see, for example, that this circle is called the circle CGH, sorry. Which is kind of strange, right? So
It is very strange.
So there's a sense in which C is unique, well, C is given, but G is kind of, you can imagine a predicate which defines G, right? The predicate of, you can imagine in the formalization, and this is indeed what you do, you introduce a predicate that's like intersect something, something. And then you have an axiom, well, you have some axioms which guarantee that there's a sort of unique point which satisfies that predicate, and then you can give it a name G. But H is not like that. It's a kind of variable point on the circle, which is only introduced in order to name the circle. So in a sense, it denotes the circle itself, although it's actually a point. I guess it's supposed to be a point anyway. So yeah, that's kind of amusing.
Why wouldn't you notate things by like the center and then like one point on the radius? That sounds a lot more natural to me.
Yeah, that's right. I would be tempted, as I kind of did, by just denoting the circle by giving a point and a line segment. This, like the circle BC, comma B or something, right?
Where did H come from?
Yeah, H, in Euclid, this is how this circle is denoted. It says, consider the circle CGH centered at B with radius BC. So H is simply introduced because 3 points determine the circle, 3 distinct points.
Right. As long as they're like non-equal, like 3 distinct points, right?
That's right, yeah. So the h doesn't play any role. It's just sitting in the diagram as it's kind of a way of sidestepping the naming convention for the circle, I guess. The circle is introduced uniquely by saying a point and a line segment, but so similarly, this outer circle is given with a k.
I think I missed a part, but there are certain points you can't use to uniquely identify a circle, and they include, like from last week's construction, if you had an equilateral triangle of points, then I think the circle could go either way or a third way. There are 3 possible circles.
That's right.
Most points should be okay.
Yeah, that's right. So you'd have to specify a point and a line segment, like which end of the line segment to have as the center, right?
Yeah, that's right. Or 3 points where they don't form an equilateral triangle, or they're not like overlapping or something. Right. That should probably do it.
Cool.
Wait, are you saying you can have 3 distinct points that define 2 circles?
Yeah, 3 circles if you have an equilateral triangle. So that's kind of last week's construction. If you can remember that diagram, that was like, you can imagine imagine you've got your 2 points, and you've got a circle for both.
You're taking one of the points as the center. Is that right? All right. I was thinking of like 3 points define the circle for which those 3 points are all on the radius, all on the circumference of the circle.
Yeah, maybe I'm going to cut you guys off because I want to get through more than one proposition per session. So I'm just going to quickly do proposition 3. So I'm over on the other set of boards now. So for 2 given unequal straight lines, to cut off from the greater a straight line equal to the lesser. So hopefully it's clear to you from the previous 2 propositions what to do here. Okay, so let AB and C here denotes the line, so that's playing a similar role to the the H and the K previously, and let's say AB is over here. So there's a total order on lines by length. That's part of the common notions. Let ABC be the lines with AB greater. Then we can construct, so by proposition 1.2, let AD be a line at A the same length as C. So let's say here. The circle at A of radius AD meets AB at E. Okay, then AE is equal to AD and thus to C, and so EB is the desired line. It cuts off from AB a straight line of length equal to C.
Nice.
Yeah, I think this is pretty interesting because I think I'd highly recommend going through this proof, but doing it where you don't allow yourself to cite proposition 1.2. So actually construct in this diagram all the intermediate circles and lines that you need to do this directly. So without citing proposition 1.2. So to do that, you'd have to construct a bunch of equilateral triangles. You'd have to construct an equilateral triangle at A in order to get AD, and so on. And this diagram will get more complicated than you might think. So this is an illustration of how important lemmas or intermediate facts are in mathematics, right? So if you are required to prove everything from scratch at all times, the complexity or length of proofs explodes very rapidly. That's quite a fundamental fact, I think.
Is like here we've got two lines and we have the ability to like conceive of one line being greater in length than the other. I can imagine doing this construction twice to like sort of take off two segments, but I don't know, would it be like unreasonable to talk about like one line that is at least twice as long as the other or something, or like 3 times as long? Like I'm sort of introducing arithmetic here.
I think that's how it works, yeah.
What do you mean?
Well, that's a valid construction, right? So you would, whether lines are of greater or equal length, so you could perform this construction to get EB, and then you could ask, can I perform this again? That is the length of EB greater than C or not? And if not, then you could cut off another length equal to C. Yeah, and you could continue in this way to figure out the remainder upon fitting C into AB. That's later on in Euclid. I presume that's how a remainder is defined.
Can you do things like verify that one line is exactly twice the length of another? Or 3 times the length or something?
Well, sure. So you're presumed to be able to know when two lines are equal. So if EB was equal to C, then your answer would be yes.
I'm just wondering, like, to what degree can you embed arithmetic into geometry?
There's several books of Euclid that are doing exactly that. So we'll get to that.
Right. Okay. Cool.
Yeah. Yeah. So that's one of the interesting reversals of modern mathematics is that we sort of see geometry. I guess we learn it in high school in this way, but when we come to study it at university, we kind of see it as founded on arithmetic, which historically is very much backwards, right? So arithmetic was viewed as founded on this, at least until, you shouldn't ask about irrationals, right? But the theory of proportions until that point was viewed as being properly understood in the context of geometry.
I think I read a short paper about like the sort of history of the quadratic formula that spoke of like proportions.
Yeah, so the theory of proportions is one of the important parts of Euclid.
Yeah, it's like pretty surprising how the hell mathematicians got by in the day when they had like no arithmetic and no modern algebra and symbolic manipulation.
Yeah, I think I often compare it to the role of the I Ching in Chinese philosophy and intellectual life, because there's a sense in which you can get trapped by formalisms that are too beautiful and attractive, right? So the Greek geometry formalism is so powerful and so profound and achieved so much that because it can do arithmetic to a certain extent, there maybe is less of an impetus to find a different way of doing it, because at the beginning, maybe the new way looks kind of primitive, it can't really do very much. So logic was very much like that until Boole, right? And if you look at Boole's book, it's like, okay, you can do a few cute things, but this was an important step in breaking out of the old mold. And I guess the achievement of Descartes and others in approaching geometry in a different way is partly to just escape from that gravitational well of Euclid rather than the kind of genius of their inventions on their own. And the same was very much true of the I Ching and Chinese philosophy. It dominated thought for a very long time. Okay, I think that's a good place to stop. So thanks everyone, and I guess we'll move on over to the next venue for a nice surprise that Billy's got in store for you.